Good day, my dear students. In this video session, let us learn how to solve the problem on tapered bar subjected to point load considering its self weight. Let us determine the nodal displacement, stresses in each element and the support reactions for the tapered bar considering its self weight subjected to point load using elimination method and penalty method in the finite element method. Okay. Now this tapered bar is varying in width from 60 mm to 30 mm. Okay, first of all let us modify this tapered bar into two steps. As in the previous video I have explained how to modify the tapered bar into stepped bar. Okay, let us modify this tapered bar into two steps, two equal parts of each step of having equal length, that is 120 mm, that is 240 by 2. Okay. Now, by considering the average width, if you consider the average width of 60 mm plus 30 mm, that is 60 plus 30 by 2, we will get 45 mm here and 45 mm here. That is the average width of the midsection of the bar. And already we have seen and we have proved how we got this 45 mm. That is by considering this as a right angle triangle. Tan of alpha is equal to, we will get opposite by adjacent, alpha value we will get, and we want to know this distance. Then I will consider this right angle triangle, and from this tan of alpha value is same, then x by 120 and x we got 7.5 mm, that is this x is 7.5 and this is 7.5 and this is 30, so that 7.5 plus 7.5 15 plus 30 45 mm. Here we got 45 mm, sorry, this one average width, and so that this first step will become average of 60 mm and 45 mm, that is 52.5 mm, average of 60 and 45. Likewise for the second step, average width will be average of 45 and 30, that is 37.5 mm we got, and this is the width. And what is the area of each step? Area of element 1, that is step 1, will be width into thickness. Width is, we got average width 52.5 and into 1 thickness of the tapered bar given, that is in the problem given thickness of the tapered bar is 1 mm, hence we will take 1 mm, hence the area of the step 1 we will get 52.5 mm square, and area of element 2, that is 37.5 into 1, that is 37.5 mm square, that is width into thickness. Now this is how the tapered bar is modified into stepped bar like this. Let us discretize so that we will have here 3 nodes and 2 elements, since there are 2 steps, 2 elements and 3 nodes. And next let us generate the stiffness matrix for element 1. It is given by, for 1D bar element, the formula is AE by L 1 minus 1 minus 1 1, order of the matrix 2 cross 2, that already we have discussed in the previous videos. Next, stiffness matrix for element 1, you substitute the properties of the element 1, that is area of the element 1 52.5, Young's modulus given is 200 GPa, that is 200 into 10 raised to 3, length is 120, and after calculation of this ratio we got 8.75 into 10 raised to 4, 10 raised to 4 you keep outside and 8.75 inside, and write the DOF numbers 1 2 1 2 like this, because element 1 is having 2 nodes 1 to 2, 2 node numbers 1 to 2. Now next we will proceed to the next page. Let us generate stiffness matrix for element 2 similarly, and for element 2 area is 37.5, Young's modulus same 200 GPa, and length is 120, so that after calculation of this ratio we got 10 raised to 4 you keep common outside, 6.25 inside, that is 6.25 into 10 raised to 4 we got from this calculation, and 10 raised to 4 you maintain the same common outside of the matrix as in stiffness matrix for element 1, and we got this inside 6.25 minus 6.25 and so on, and write the DOF numbers 2 to 3 2 to 3, because element 2 is consisting of 2 nodes 2 to 3. Now let us generate the global stiffness matrix by assembling the two element matrices K1 and K2 since there are three unknowns, three nodes, three unknowns, u1, u2, u3, then order of the global stiffness matrix should be 3 cross 3, that is 3 rows 3 columns. You just generate a grid like this, and let us write the stiffness matrix stiffness matrix K1 terms into this 1 2 1 2 box, and next stiffness matrix for K2 terms 2 3 2 3, transfer these terms into this box 2 3 2 3, and one common term you will get in both the matrices, that is 2 2 at 8.75 and 6.25. you just add it, and the remaining whichever is blank you just write it 0. This is how global stiffness matrix we got. Now next, global load vector you find. As we know that the given tapered bar is subjected to the point load, as well as the weight density is mentioned here, that is 76.6 in 10 to minus 6 Newton per mm cube. That is nothing but we should consider the self weight also. Therefore, now we will proceed to the next page. Here you can observe, we will consider first, we will write the point load vector. Point load vector, just we will write the point load values. For node 1 it is 0, at node 1 there is no applied force. Next, at node 2 I wrote plus 100, at node 2 I wrote plus 100 because at node 2 the load acting is 100, and this load, direction of this load is in the same direction of element numbering, hence I wrote positive. Now next, at node 3 the point load is 0, there is no applied force at node 3. Okay, now come to body force vector. Body force is nothing but it is the force generated due to the self weight of the body, and that is self weight. How do you calculate? That is, weight is equal to, we know that, density into volume, weight density into volume, because weight density is equal to weight by volume, hence weight is equal to weight density into volume. Weight density I wrote here rho into g, that is mass density into 9.81, and AL is area of the element and length of the element, that will give you volume. Okay, now this rho g AL, this weight, this body force will be equally distributed to the two nodes of the element, hence we should take rho g ALE by 2, rho g ALE by 2 for both the nodes. Hence the formula for body force vector for the each element is given by rho g AL divided by 2 into 1 1. Okay, now let us generate the body force vector for element 1 by substituting the data rho g A1 L1 by 2, okay, into 1 1. Now what is rho g? Rho g is the weight density. Already the given value is in terms of weight density only, that is in Newton per mm cube. Hence if it is given in kg, then you should convert it into by multiplying it by 9.81. Now the given value is already in Newton per mm cube, then directly you substitute that value, no need to convert. And next, area of the element 152.5, length of the element 120. Next, if you calculate this ratio, we will get 0.2413, 0.2413, that is inside the bracket I wrote 1 1 into 1. Okay, and for DOF numbers you write 1 2 1 2, because element 1 consisting of two nodes 1 to 2. Now next, similarly body force vector for element 2 you calculate rho g A2 L2 by 2, rho g, that weight density is same, the same material, and next area is 37.5 mm square, 120 is the length, and into 1 1. By calculating this ratio, we got 0.1723, 0.1723, 0.1723 you write, and write the DOF numbers 2 3, because the element 2 is consisting of two nodes 2 to 3. Now next we will proceed to the next page. Now we will write the global body force vector at the three nodes, that is at the node 1 0.2413, okay, that is here, as we know here, as we got this one DOF number 1 value 0.2413, but here in this there is no 1 value, DOF number 1 value, we will write 0.2413. In this body force vector, second DOF number 0.2413, as well as in this body force vector also second DOF number is 0.1723. We will add up, and third DOF number is 0.1723 value. Hence we will write first DOF number value is 0.2413 and second DOF number value 0.2413 plus 0.1723, because in both the body force vectors it is available, and third one is 0.1723. Now next, if you add up, you will get 0.2413, 0.4136 and 0.1723. This is the body force vector. Now these are the weight, that is body forces acting at these three nodes. Now global load vector, by combining point load vector and the body force vector, by combining, here we got point load vector 0, 100, 0. We will combine, will assemble these two, 0, 100, 0, this one point load vector, and we got body force vector, this one. If we add up 0 plus 0.2413, 100 plus 0.4136 and 0 plus 0.1723. This is what the global load vector we got. Global equilibrium equation, Ku is equal to F. Already global stiffness matrix we have calculated. Just write it into unknowns U1, U2, U3 is equal to F is these values 0.2413 and so on. Okay. Now next we will move on to, we will apply now elimination approach to determine the unknown nodal displacements U1, U2, U3. Since node 1 is fixed, it is consisting of supports, it is provided with support, hence U1 is 0. Eliminate first row and first column. Hence remaining two equations only, the eliminate first row and first column, remaining two equations only have to be solved. Okay. Now what are these two equations? If you consider in the remaining two equations, if you consider first term also 0.875, 8.750, it is into U1. U1 is already 0. Neglect this first term, and in the second equation and third equation you consider only these terms. Okay. Now 10 raised to 4 outside, 15 into U2 minus 6.25 U3 is equal to 100.4136. Next equation, minus 6.25 U2 plus 6.25 U3 is equal to 0.1723. That is 10 raised to 4 outside, that is the common. Now next we'll go for solving these two equations. As you have seen, I have solved these two equations. We will get U2 is 0.001149 mm. That is the displacement at node 2 at the midsection of the tapered bar is 1.149 into 10 raised to minus 3 mm. And next, by substituting this U2 value into one of these two equations, we will get U3 value 0.00115 mm. That is displacement at the node 3 at the right end is 1.15 into 10 raised to minus 3 mm. Now next we will move on to the stress in element 1. Now we will move on to the stress in element 1. Let us find the stresses in each element. Stress in element 1 is given by Hooke's law, that is Young's modulus into strain. Young's modulus is 200 GPa into strain is change in displacement between the two nodes, that is U2 minus U1 divided by length of the element L1. Substituting these U2 and U1 values, just now we got U2 value as this one and U3 value is this one, U1 is 0. By substituting these values we will get the stress in each element. So that we got sigma 1 1.915 Newton per mm square, that is in element 1 the tensile stress of 1.915 Newton per mm square is induced in element 1, and Similarly, stress in element 2 is given by E into strain for element 2. Young's modulus is same, and strain in element 2 is change in displacement between the two nodes 2 to 3, that is final node U3 minus U2 divided by L2. Substituting U3 and U2 and L2 value is 120, we will get stress in element 2 0.00316 Newton per mm square. And next, the support reactions by using elimination approach, the formula R is equal to Ku minus F. Now since the support is provided at node 1, the reaction force exists at node 1 only. R1 you calculate by considering the first equation of the global equilibrium equation, that is this one. First equation you use, you refer, that is 8.75 U1 minus 875 U2 plus 0 minus 0.2413. That is the first equation. To find R1, R1 is equal to 10 raised to 4 outside into 8.751 minus 8.02 plus 0.83 minus 0.2413. This is force Ku minus F1. Next, if you calculate, you will get reaction force at node 1 minus 100.77 Newton. Since the applied force is 100 Newton, and the reaction force we got minus 100.77. It is verified and it is correct. Now next, these are the displacement values. We got U1 0, U2 1.14 in 10 raised to minus 3 and U3 displacement values, and also we have calculated the stress in each element and support reaction by using elimination approach. Now we will proceed to penalty approach. The penalty approach can be applied to determine the unknown nodal displacements. Okay, up to global equilibrium equation the procedure is same for elimination or penalty. Now I will write the same global equilibrium equation we got, the same up to this much. The solution is correct. Okay, solution is the same solution you have to follow. Now I will write this equation, Ku is equal to F. Now how to apply the penalty approach now? In this, we are not eliminating any of the equations like in case of elimination. In penalty approach, we are not eliminating any of the equations, just we are increasing the stiffness value across the support. That is every support is modeled as a spring. It is modeled as a spring. Support is modeled as a spring of having large stiffness value C. Okay. Now that stiffness value we need to calculate. Since this stiffness value across the support is increased in such a way that so that the displacement value we will get the accurate. That is how. Now here in case of penalty approach, we are not eliminating any of the equations. We have to increase the stiffness value, C value, across the support only. If we increase the stiffness value, what will happen here? We know that Ku is equal to F is that. Okay. If I write K is equal to F by U. Okay. If we increase the stiffness value, then the displacement value goes on decreasing and the force value goes on increasing. That means if we need to increase the stiffness value in such a way that increase to such extent so that displacement value will come to 0 in this case. That is at node 1 it should come to 0 because we are not eliminating any of the equation. We are calculating all the values U1, U2, U3. U1 we should get nearer to 0 because we know that U1 is 0. Hence we should increase the stiffness value across this term at K1, K11. These are all the stiffness values. This K11 represents the stiffness value at node 1. We should increase it so that the U1 value should reduce up to 0. And also it will affect, if we increase the stiffness value, we will get F1 value also will increase. How to do that? First you should calculate C value, last stiffness value. Okay, it can be calculated by using the formula C is equal to maximum of mode Kij. That is this Kij matrix we got global stiffness matrix, maximum of Kij into 10 raised to 4. What is the maximum value among this Kij global stiffness matrix? That is 15 into 10 raised to 4. This is the maximum value. Then maximum of Kij value in this global stiffness matrix is 15 into 10 raised to 4 into 10 raised to 4. This is the C value we got, and that we get 15 into 10 raised to 8. This is the C value. This is how we have to calculate the stiffness value. Into 10 raised to 4, this is the experimentally found correct value 10 raised to 4. You may go for 10 raised to 5 or 10 raised to 6, but these values are not experimentally found correct values. These are not experimentally found correct values because these will not give the accurate result. Hence, the 10 raised to 4 it should be multiplied with maximum of Kij. We got 15 in 10 raised to 8. Now, this C value. Now, since the boundary condition is node 1 is fixed, hence add up this C value to K11 term because node 1 is fixed. If node 3 is fixed, then add up the C value to K33 term. Okay, here in this case node 1 is fixed, then add up C value to K11 term and also add up CA1 to F1 term like this. These two have to be modified because as I told you, if you increase the stiffness value, displacement goes on decreasing and it will affect force to increase. Hence add up the CA value to F1 term, CA. Okay, what is this CA? CA is nothing but that is the force generated on the spring. Stiffness into A is specified value of the displacement at that spring. Is there any specified value of the displacement? That means at node 1 there is no gap provided here like this. Is there any gap provided here? No. Okay. Now in this case there is no gap, then A1 is 0. A1 is nothing but that is the specified value of the displacement across the spring, that is across the support. It is modeled as spring. Okay, A1 is 0 and A1 is 0. Okay, now we will add up the value of C to K11 term. Okay, what is K11 earlier value? 8.75 10 raised to 4, 8.75 10 raised to 4 plus C value is 15 into 10 raised to 8. Now 10 raised to 4, since it is common here, then 10 raised to 4 outside, inside you will get 8.75 plus here the common you will get 15 into 10 raised to 4, that is 15 0000. Now therefore K11 term 10 raised to 4 outside, if you add up these two you will get 15008.75. Okay, the next F1 will become F1 plus CA1. Okay, what is CA1 is 0. How it is? A1 is 0, then C into A will be 0. The 15 10 raised to 8 into 0 will become 0. Hence F1 earlier value was 0.2413, which will become same. Okay, now we will modify the global stiffness matrix. Just we will modify K11 term, we will replace. I will replace by new term by adding up of value of C 15008.75, and next I will write new value of F1, that is same 0.2413. Next now after this modification, solve all the three equations. Solve all these three equations to get the values of U1, U2, U3. If you solve these three equations, all these three equations, you will get U1 as 6.7 into 10 raised to minus 8 mm, which is equivalent to 0. That is 0.000008067 mm. Okay. Next U2 value we got 0.001149 mm, and U3 displacement value at node 3 0.0015 mm, which is the same as these U2 and U3 values are same as in case of elimination approach. If we check it here also In case of elimination approach, we got 0.0011 and 0.00115, 114 and 115 mm, and here also we got in penalty approach also the same values we got 0.001149 and 0.00115 mm. Okay, this is how using penalty approach we are not eliminating any of the equations. We should solve all the equations, but we should modify the terms of the stiffness matrix and force vector by adding up the value of C to the support stiffness values. Okay, now let us calculate the stress in element 1. The procedure is same by using Hooke's law, Young's modulus into U2 minus U1 by L1, that is strain in element 1. What is U2? This value we should substitute, and U1 value we should not substitute here 0, we should substitute this value. Okay, although we will get same result. L1, that is length of the element 1, is 120. If you calculate stress in element 1, we got same as elimination approach, 1.915 Newton per mm square. Next, sigma 2 also if you calculate, you will get there 0.0036 we got, it is approximately 0.004 Newton per mm square we got. Okay, U3 minus U2, you substitute these values. Okay, and L2, that is 120. The same way if you calculate, you will get stress in element 2 like this. Now support reactions by using elimination by using penalty approach. How to calculate the support reactions? R is equal to minus C into U minus E. That is, R can be calculated as minus C into, that is stiffness into displacement, U minus E. What is that U minus E? U is the displacement value for the support which is modeled as a spring, and A is, if is there any gap provided here. There is no gap at the support, hence A we should use 0, that U minus E. Okay, now this is the formula you should use. Okay, since support exists at node 1, then R1 you calculate. R1 is equal to support reaction minus C U1 minus E1, because we are calculating R1. If you are calculating R3, here it is not here there is no support at node 3. If suppose for example say at node 3 if you want there is a support, then R3 can be calculated by using by minus C U1 U3 minus A3, like that. But here in this case support exists at only at node 1. R1 is equal to minus C U1 minus A1, and R1 is equal to minus C U1 only you will get, because A1 is 0, because there is no gap at this across the support. Now R1 is equal to minus C. What is C value? 15 into 10 raised to 8. Already we have calculated C value, that is 15 into 10 raised to 8. Okay, now next. Okay, now minus 15 10 raised to 8 into U1 value already we calculate 6.7 into 10 raised to minus 8. You should not substitute here 0, because using penalty approach we got this value. You should substitute that value, and here by calculating this we will get R1 is equal to minus 100.5 Newton, which is as same as elimination, that is minus 100.7 Newton. Okay, this is how we can apply the penalty approach and elimination approach. Either in the examination, if you are asked to solve the problems on bars to determine the nodal displacement, stresses in each element and support reactions using FEM, then either you use elimination or penalty approach. If it is not asked specifically which approach has to be used, then you use elimination approach, that will be convenient to you. If penalty approach is asked specifically in the problem, then you should solve the problem using penalty method only. Okay, I hope you have understood the this one problem, and your assignment is the previous question paper VTU question paper problems on bars, tapered bars. You solve it. Okay, if you have any doubts, let me know, and I will try to clarify your doubts. Thank you, dear students. Thanks a lot. Take care. Stay safe. Stay healthy.